The robot that learned tennis. The Innovation Attorney, March 2026. In March 2026, a humanoid robot stood on a tennis court in a laboratory in China, tracked an incoming ball traveling at speeds human recreational players routinely produce, shifted laterally across the baseline, and returned the shot with a forehand stroke that landed within 2.5 meters of a designated target zone. It did this 96.5% of the time. It had never received a lesson from a professional. Its training data came from amateurs. The system is called LATENT, learning athletic humanoid tennis skills from imperfect human motion data. The research team at Galbot, a Chinese AI robotics company formerly organized as Galaxy General Robotics, designed it around a principle that cuts against decades of conventional thinking in robotic motion learning. You do not need perfect data. You need the right architecture. The problem that stopped everyone else. For years, the dominant assumption in robot learning for athletic tasks was that you needed kinematically feasible, physically accurate, expert-quality motion capture data as reference trajectories for the robot to imitate. Collecting that data was expensive and time-consuming. Extracting it from video was computationally intensive and frequently produced sequences that a robot body, with its different mass distribution and joint limits, simply could not execute. The result was a field that progressed steadily on constrained tasks in structured environments, but stalled when it encountered the full complexity of real athletic play. Whole-body locomotion combined with fast, precise manipulation, coordinated in real time against an unpredictable moving target. Tennis concentrates that complexity in one sport. A successful return requires the robot to estimate the incoming ball trajectory from sensor data, plan a path across the court, execute bipedal locomotion fast enough to reach the strike zone, select the correct stroke mechanics, and complete the swing with enough precision to place the ball in a target area. All of this must happen in the fraction of a second between when the ball leaves the opponent's racket and when it arrives at the robot's position. Prior systems addressed subsets of this problem. None addressed it as a single integrated whole-body control challenge with imperfect training data. What LATENT actually does. The LATENT pipeline proceeds through 3 stages, each building on the last. In the first, a motion tracker is pre-trained on 5 hours of primitive skill fragments collected from amateur players using a compact motion capture system. The data captures forehand strokes, backhand strokes, lateral shuffles, and crossover steps in isolation. These fragments are incomplete, imperfect, and not synchronized with live ball interactions. Crucially, right wrist signals were excluded from tracker training, and deliberate perturbations were introduced to force the system to function even with degraded or missing channels. Imperfection was not a bug to be corrected. It was a design parameter. The second stage is where the research makes its most significant technical contribution. Using a conditional variational information bottleneck and a diffusion-based generative model, the system compresses the learned motion tracker outputs into a compact latent space, a mathematical representation that captures the statistical structure of human primitive tennis skills without requiring those skills to be complete or expert quality. The diffusion model learns the distribution over these latent primitives, enabling the system to generate plausible motion continuations from incomplete inputs and to smoothly interpolate between discrete skill states. The latent space is specifically designed to be correctable, a high-level reinforcement learning policy. Trained in the third stage using MuJoCo simulation with multi-GPU parallel processing, learns to apply directional corrections within this latent space in response to live ball observations. The latent action barrier governs how far the policy can deviate from the prior distribution of human motion, balancing the naturalness of the robot's movements against the task-optimal adaptations required to return a specific incoming ball to a specific target location. The policy does not choose between looking human and performing well. It does both simultaneously, within a principled mathematical constraint. The numbers and what they mean. The evaluated performance is striking. 96.5% overall success rate across 10,000 simulation trials, forehand returns succeeding approximately 90% of the time in real-world testing, backhand returns approximately 80% of the time, and sustained multi-shot rallies against human opponents. The system outperformed prior methods in success rate, ball placement accuracy, and motion naturalness. It deployed on the Unitree G1, a commercially available humanoid robot standing 1.32 meters tall, weighing 35 kilograms, fitted with 29 degrees of freedom, and joint actuators capable of 120 Newton-meters of torque. Consider what these numbers represent beyond the sport. Prior humanoid robotic systems demonstrated athletic-adjacent capabilities in carefully bounded conditions. Table tennis on a fixed platform, simple bipedal locomotion on flat terrain, basic object manipulation in slow, structured settings. LATENT is different in kind, not just in degree. It integrates full-body locomotion across an unpredictable playing surface with high-speed, high-precision upper-body manipulation, coordinated by a policy that learned from cheap, imperfect data and transferred to a physical robot without catastrophic failure. The robotics community has been working toward this integration for decades. The open question that matters most. The current LATENT deployment relies on an external optical motion capture system to track the global position of both the robot and the ball. Retroreflective markers on the robot body and reflective tape on the ball feed position data to the capture infrastructure, which provides the millimeter-level accuracy that a high-speed control system requires. This is a significant practical constraint. A tennis-playing humanoid that requires a laboratory-grade motion capture volume to function is a research demonstration, not a deployable product. The question of whether the LATENT architecture can achieve equivalent performance using only onboard sensors, the Unitree G1's LiDAR, depth camera, and IMU, is unresolved. It is also, arguably, the most commercially significant question in this research program. If yes, the path from laboratory to product becomes substantially shorter. If no, the bottleneck shifts from algorithm design to sensor and compute infrastructure, which is a different and potentially more tractable engineering problem than the learning architecture challenge LATENT just solved. The full LATENT codebase, including the motion tracker pre-training pipeline, the online distillation framework, and the high-level policy training code, is open source on GitHub under Galaxy General Robotics. A small subset of retarget human tennis motion data is included. The companion OpenTrack repository provides the underlying motion tracking infrastructure. The research community now has the architecture. The hardware is commercially available. The data collection methodology is cheap enough for any well-equipped university lab. The combinatorial implication for how quickly this technology advances is not difficult to calculate. Humanoid robots that can learn athletic skills from imperfect data, transfer those skills to physical hardware, and perform them reliably against live human opponents represent a qualitative threshold in what these systems can do. The sport of tennis may be the proving ground. The applications that follow will not be confined to courts. Interested in analysis about the intersection of tech, policy, and the law? Check out my Substack channel, https://theinnovationattorney.substack.com.